Okay, so cardiovascular system has two parts, the heart and the blood vessels, and we are talking about the heart. Today we will continue to talk about the heart. So in today's lecture, first we will talk about the physiological properties of heart muscle. Physiological means functional properties of heart muscle. You know that heart muscle is different than other muscles of our body, right? So why heart muscle is different? What are the special properties, functional properties the heart muscle has? We'll talk about that. Then we'll talk about the mechanisms of contraction of cardiac muscle. Cardiac muscle contracts and relaxes. So what is the underlying mechanism of contraction of cardiac muscle? We'll talk about that. Then we'll talk about the conductive system of the heart. What is that? Inside the heart, we have a very highly specialized tissue. Inside your heart, you have a very highly specialized tissue structure, and that tissue is called the conductive tissue. Okay, and the system formed by that tissue is called the conductive system of the heart. And what's the function of conductive system? Conductive system performs two functions: generation of electrical impulse, production of electrical impulse, number one. Number two, transmission of electricity or electrical impulse. Okay, so that's why it is called the conductive system. Conducts the electrical signal. So production and transmission of electrical signal, and that is done by a very highly specialized tissue inside the heart. We'll talk about that. Then we'll talk about the regulation of heartbeat, how the heart rate is controlled, how the heartbeat is controlled. We'll talk about that. And then we'll talk about the electrocardiogram or ECG or EKG. Some people say EKG, some people say ECG. ECG is more common in European countries. In America here, we use EKG more. Okay? So anyway, so electrocardiogram, we'll see the events or components of an EKG. Then we'll talk about abnormal heartbeat, irregular heartbeat. Before we talk about the functional properties of cardiac muscle, I'll briefly talk about the large blood vessels attached to the heart. You know that a number of large blood vessels attached to the heart. We'll talk about those blood vessels. So we have talked about systemic and pulmonary circulations in last class, right? We have talked about that. So it will be easy for you to understand what are the large blood vessels and their functions. So let's start from pulmonary circulation. We know that right side contains the deoxygenated blood and left side contains the oxygenated blood. So this is and we also know that atria receives the blood from outside, right? And ventricle does what? Pumps the blood to outside. Okay, so this is the right ventricle that contains deoxygenated blood, and right ventricle contracts and sends the blood, deoxygenated blood, to the lungs through the pulmonary arteries. But from the right ventricle, first the large artery arise, that is the pulmonary trunk. So pulmonary trunk is attached to the right ventricle and receives blood, deoxygenated blood, from right ventricle. So this is the pulmonary trunk. And pulmonary trunk is very short and wide. And then pulmonary trunk divides into right and left pulmonary arteries. Okay? Right and left pulmonary arteries. And then pulmonary arteries divide into two branches. So these are also the pulmonary arteries. So left pulmonary arteries, right pulmonary arteries. And they will take the blood to the lungs, deoxygenated blood. Then inside the lung, the blood will get oxygen, right? And will come back to the heart. But oxygenated blood will come back to which side, right or left? left side, right? Left side deals with oxygenated blood. So after the blood gets oxygen inside the lung, the oxygenated blood will come back to the left side of the heart. Is it clear? And who will receive the blood there? Atrium or ventricle? Atrium. So left atrium will receive the oxygenated blood from the lung, and who will bring the oxygenated blood from the lung to the left atrium? Those are the pulmonary veins. So that's why you see that pulmonary arteries, we say, carry deoxygenated blood, and pulmonary veins carry oxygenated blood. It's opposite of systemic circulation. In case of systemic circulation, arteries carry oxygenated blood and veins carry deoxygenated blood. Okay. Now, that's the pulmonary circulation. Now, from left atrium, the oxygenated blood will go to the left ventricle. Always remember, from the atrium, the blood will go to the ventricle. Right? From the atrium, the blood will go to the ventricle. So atrium has two functions: receiving the blood from outside and sending it to the ventricle. Those are the two functions of atrium. Okay? So atrium will receive the blood from outside and will send it to the ventricle. Okay? And then ventricle will pump the blood out. And left ventricle will very strongly, forcefully pump the blood out, oxygenated blood, through the aorta. So aorta is attached to the left ventricle, and blood will go that way out from the left ventricle. First it will enter into the ascending part of the aorta, then pass through the aortic arch, and then descending aorta is very long, runs behind the heart and goes all the way down to the abdomen. Okay, so ascending aortic arch and descending aorta. And those are the parts of the aorta. So aorta will distribute the blood through many branches throughout the body. So oxygenated blood will run throughout the body and deliver the oxygen to the tissues everywhere in our body and collect what? Carbon dioxide, right? So oxygenated blood will deliver oxygen and receive the carbon dioxide, collect the carbon dioxide and become deoxygenated, right? And then deoxygenated blood from the body should come back in which side, right or left?
Right.
Right, because right side deals with deoxygenated, right? And who should receive of atrium or ventricle? Atrium, is it clear? So right atrium will receive deoxygenated blood from the body, okay? And two large veins will bring the blood back into the right atrium. What are those? From the upper part, from the upper part of your body, superior vena cava will bring the deoxygenated blood to the right atrium, and from the lower part of the body, inferior vena cava will bring the blood. So both superior and inferior vena cava drain the blood, deoxygenated blood, into right atrium. Make sense? So that's why both are connected to the right atrium. So superior and inferior vena cava are connected to the right atrium. Aorta is connected to the left ventricle. Pulmonary trunk is connected to the right ventricle, and pulmonary veins are connected to the left atrium. Okay, now we'll talk about the functional properties or physiological properties of cardiac muscle. Cardiac muscle is different than other muscles of our body. Cardiac muscle has one important property is contractility. That means we know that cardiac muscle can contract and relax. That ability to contract is the contractility. Autorhythmicity. Auto means self and rhythm indicates regular interval. So heart muscle can contract how? At regular intervals. Your heart will not contract like this. See here. If this is your heart will not contract like this and then like this or this. That is not normal, right? Heart beats like in regular intervals. That is very important. And we don't send any signal to the heart. We don't tell the heart that you contract now. it will does automatically. So auto is self and rhythm is regular interval. Heart will beat at regular interval by itself. That is the auto rhythmicity. Okay. Conductivity. As I have mentioned already, that inside the heart you will find very highly specialized tissue, conductive tissue. Okay, and conductive tissue performs two functions. I say two functions. One is production of electrical impulse and transmission of electrical impulse. Okay, so because of the presence of conductive tissue or system in the heart, those two things happen. Syncytium, heart muscle. All muscle fibers or cells of the heart work together as a single unit. That is the syncytium. That means the whole heart works as a unit, as a whole. Make sense? Whole heart works as a whole, and as a single unit. That is the syncytium. Now, how the whole heart works as a whole? Because of the presence of two types of junctions, intercellular junctions, desmosomes and gap junctions. Okay, in heart muscle you will find plenty of desmosomes and gap junctions. And because of those two junctions, heart muscle or heart work as a single unit. Now, why? Desmosomes, probably you remember from NP1, we have talked about different intercellular junctions. Do you remember? Tight junctions, gap junctions, desmosomes. And desmosomes connect the cells, hold the cells very strongly. It's like zipper in your cloth, very strongly. So all heart muscle fibers are very strongly attached or held to each other, very strongly. Make sense? So now you see what happens. If one heart muscle fiber contracts, then other heart muscle fibers will contract because they are attached to it, right? Both sides. So no one will be able to work individually. They have to work together, all of them. It's like you all are holding your hands each other very strongly. Now, if even 2 or 3 of you are very lazy, you don't want to move, you have to move, right? Because everybody is moving. So all heart muscle fibers or cells are very strongly held together, attached to each other, so they will all work as a single unit, as a whole. Okay? So that is because of desmosome. Now, the gap junctions, if this is one heart muscle fiber, this is the next one, and gap junctions are also present in between the cells, and gap junctions, you know that, have many holes through, and through those holes the fluid or ions can move from one cell to the next very easily. So there is gap junction here, so this is another muscle fiber, there are holes. Okay, so if any change occurs inside this, it will quickly go to the next one through the holes. Okay, the information will go, the change will be transmitted to the next cell. It's like many rooms, and if you keep them, separated completely, then you won't be able to talk to each other, communicate with each other. If the all doors are open, then you can easily talk to each other. If any change occurs in the air here, it will go to the next one, right? So all heart muscle fibers will get the information if any change occurs inside any muscle fiber. So they can communicate, talk to each other very easily, and that is another reason the whole heart works as a syncytium, or a single unit, or as a whole. Absolute period. Instead of absolute period, I would like to say refractory period. So change it to refractory period. Okay. So refractory period is another important property of cardiac muscle. What is that? Refractory period, also called RP. Okay, commonly used RP or refractory period. What is that? During the contraction of the heart, see how it is contracting. During the first part of the contraction of the heart, if you give any external stimulus to the wall of the heart or to the muscle of the heart will not listen to that at all. Heart will completely, absolutely ignore that. Okay, I am repeating again. During the first part of contraction of the heart, if you give any external stimulus, heart will ignore that completely, will not listen to it at all. That is the absolute refractory. Absolutely no. Absolutely not listen, will not listen. Okay? So that is called absolute refractory period. It will not listen at all. Now, during the last part of contraction, end part of contraction, if you give an external stimulus to the wall of the heart may or may not listen. So, how does it may or may? If the stimulus is strong, heart will probably listen, respond to that. If the stimulus is weak, heart will not listen, right? So it is relative or absolute? Relative, makes sense? Depending on the strength of the stimulus, right? If it is strong, heart will listen. If it is weak, heart will ignore it, right? But first part is what? Heart will absolutely not listen. So that's why it is called absolute refractory period. And second part of contraction is relative refractory period, the time when heart may or may not listen. Okay, so that's the relative refractory period. Make sense? Okay. So very important property of cardiac muscle is refractory period. Why? You think that your heart is contracting and the pump of the blood is completed, 80% of pumping is completed during the first part of contraction, like 80% of the blood will get out during the first part of contraction, okay? So now when the heart is contracting, if you give an external stimulus, you know that a lot of hormonal changes are being taken place, right? Neural signal is being created inside the body. Now if your heart listens to that, then what will happen? During the contraction of the heart may stop contracting or do something else, right? So is that good? Dangerous, right? So during the first part of your heart contraction, it should completely ignore any external stimulus because it should pump the blood out. Now when 80% of the blood is already out, the last part of contraction, if the stimulus is strong, heart may listen to that. That will not really be dangerous, right? Because most of the blood has already gone out. So that's why the refractory period is very important, is a very important property of your heart, yes.
It's not clear to me what do you mean, what's the stimulus? What?
Very good. So stimulus is, it could be chemical stimulus, electrical stimulus, mechanical stimulus. If I poke you with something pointed, very sharp, that is mechanical stimulus.
Right.
Okay? If I put some chemical on your tissue, that's the chemical stimulus. Make sense? If I put electrical signal, stimulus, then that's electrical. So inside our body, you know that chemical changes occur, right? Chemicals are being released. And some of those chemicals work on the muscle tissue.
Okay.
So if heart listens to that, then it would be, your heart function will not be normal, right? If it listens every time. If you know that sometimes nerve impulses are being created inside the body, right? If that tells the heart, goes to the heart, and heart listens to it, it will be dangerous.
So what's the ideal behind, when you have a heart attack and they put the paddles on you, it will absolutely not listen to?
That is
In the
not
beginning?
normal, that is abnormal condition, okay? That is
Okay.
abnormal condition.
Okay,
Uh,
this is under normal condition.
Yeah, normal condition, okay?
Okay.
Okay, so that's the effective theory. Elasticity. Heart muscle has elastic property. What is that? The ability to get stress and recoil. That is the elasticity, right? If you put pressure, it will get, if you pull it, it will get longer. And when you release that pressure, remove that pressure, it will come back to its actual shape, recoil. That is the elasticity, right? So the ability to get stress and recoil, that's the elasticity, and heart muscle has that property. That's why heart gets bigger and smaller, because of that elasticity, right? Elastic property of the cardiac muscle. And there is a law about that, the elasticity of the heart muscle. That law is called Frank-Starling law. What is Frank-Starling law about elasticity? The Frank-Starling law is very simple. It says that the more you will put the pressure, the length will be more. That is simple, like elastic thing you use in your clothes. If you put more pressure, pull strongly, then it will increase in length, right? So the length is proportionate to the pressure. So when you increase the pressure, the length will increase, okay? So that is the Frank-Starling law. Now, that is the first part of Frank-Starling law. The second part is when the heart muscle is within the physiological limit. That means within the physiological limit, if you increase the pressure, the length will increase. It is, again, you think about the elastic thing you use in your clothes. If you pull, it will get longer, right? It will get longer. Now if you put too much pressure, keep doing that, then at some point, it will lose the elasticity. It will not come back to its actual shape, right? And if you use too much, you know that it gets lose the elasticity, right? So the length will increase proportionate to the pressure within the limit. There is a limit. If you keep putting pressure increasing, then at beyond certain limit, it will not follow the Frank-Starling's law. Okay, so that's the Frank-Starling law of elasticity. A simple law. Okay, now we'll talk about the mechanisms of heart muscle contraction. So to understand the mechanism of heart muscle contraction, you have to understand the depolarization and repolarization. So what is depolarization?
Moving away from.
Yeah, if this is your heart muscle cell, okay, yeah, you will measure the voltage inside the cell, inside the muscle fiber or inside the cell. You will measure the voltage, electricity, and before the heart muscle contracts, what happens? Depolarization must occur. If depolarization doesn't occur, heart muscle will not contract. Okay? So, how depolarization occurs? The sodium channels get opened. Okay? So, sodium is positive or negative?
Positive.
Positive, very good. So, sodium channels will get opened. And always remember, very important basic information, that inside the cell of our body, the concentration of sodium is less. Outside is what?
Higher.
Higher, more. This is true for all cells of our body. Outside of the cell, the sodium is higher. Inside the cell, the concentration of sodium is lower. Keep that in mind. Another information you need to keep in your mind, inside the cell, the potassium concentration is always high, and outside is what? Low. Okay?
Inside all cells?
All cells, yeah. This is true for all cells, that outside sodium is high and inside potassium is high. This is very basic information, okay? You need to know that. Okay, now these are the sodium channels. What will happen during depolarization? The sodium channels will get opened. Okay, so which way the sodium will move? From outside to inside or inside to outside?
Outside to inside.
Because the concentration is
Is higher
higher
outside.
in outside. We know that that's the basic diffusion. That from high concentration, the solutes will move to low. So when the sodium channels will get opened, sodium will get in. Now, I told you we are recording the voltage inside the cell. So now if I draw here, this is the resting condition when all the channels are closed. This is the resting membrane potential, okay, in resting condition. Now during depolarization, sodium channels will get opened. So what will happen? Sodium will rush in, right?
Yes.
So now if this is positive, this is negative, which way the membrane potential will move? Membrane potential means inside the cell. Towards positive or towards negative?
Towards positive.
How about this side?
Towards positive.
Inside the cell will become more positive because positive is getting in, sodium is getting in, make sense? So it will move upwards, right?
Correct.
Okay, so that is called depolarization. So the voltage inside the cell or inside the fiber is changing towards positive. That is the depolarization due to the opening of positive channels, sodium channels. Okay. So remember that. If you see this graph, you see the depolarization is here. Okay, number one is depolarization moving towards positive. If you go downwards, that means moving towards negative. Okay. So first, depolarization occurs due to the opening of sodium channels. Now, what type of sodium channels? There are two different types of sodium channels. One is called voltage gated, another is non-voltage gated. Okay. So let me talk about that. So two types of sodium channels. We have voltage gated and non-voltage gated. Okay, sodium channels. Sodium channels. Okay. Now remember that voltage gated sodium channels open extremely fast because it is controlled by the electrical impulse. So very abrupt, very quick, very fast opening of all the channels. Okay. So that is voltage gated. Okay. Non-voltage is slow, gradual opening of sodium channels. Okay. Did you get the difference? Okay. In case of voltage, all sodium channels will open very fast. Now, if this is the time, this way, time, and I show you two depolarization. One is here, another is here. Which one is due to voltage gated?
First.
This one is fast, right? Time is here, very fast. So it will move very fast towards positive. And this one, the channels will open slowly, so it will take more time to move towards positive, right? Take more time. So in case of cardiac muscle, the sodium channels will open by voltage gated. So sodium channels are voltage gated sodium channels. So that's why you see the depolarization is not slow like this, it is very fast. Okay. So here in this curve you see very fast rise of positive depolarization. Then next what will happen? Next the sodium channels will get opened. Okay, sodium channels will get sodium channels will get closed because depolarization is complete. Sodium channels will get closed, and potassium. What will happen? Sodium channels will get closed, but the calcium channels will get opened. At the same time, what will happen? The potassium channels will get opened. Now you tell me, where the potassium is more, inside or outside? Inside is more, right? So which way the potassium will move?
Out.
Outwards. Okay, so calcium and potassium, both channels will be opened, but calcium will move inwards and potassium will move outwards. So they will basically cancel each other. Inside the cell, if you measure, then the change will not be seen, because positive is leaving, positive is getting in, right? So you won't see much change in the voltage inside that cell. And that's why you see this part that is called the plateau. Formation of plateau after depolarization. Next phase, phase 2, is plateau, when the voltage will stay almost same. It will stay like this, okay? Because calcium is getting in, positive is getting in, potassium is getting out, okay? So you won't see much change. Then what will happen? The calcium channels will get closed, so no more calcium is getting in, but more potassium will get opened. So what will happen? More potassium will get out, right? If positive only gets out, then it will move towards the negativity, right? Losing the positive, so it will go down. That is the repolarization due to the opening of potassium only. So we have seen how the depolarization occurs in cardiac muscle, how the plateau is formed, and how repolarization occurs. Okay. Now, depolarization must occur for the contraction of the heart muscle, and repolarization must occur for the relaxation. So depolarization indicates contraction, repolarization indicates causes relaxation. Now, why the plateau is important here? You know that we need little bit time between the contraction and relaxation, right? They should not overlap. Contraction, then little bit time, then relaxation. And that plateau will provide that time. During that time, nothing will happen, okay? So that is very important. So red line is it showing the contraction and the contraction and relaxation. Contraction is after the depolarization and relaxation is after the depolarization. Okay?
In the heart, there's we learned about it before. There's a phase when they're a little hyperpolarized, like they actually go below. Does the heart do that as well, or does it always return to?
Yeah, so this is depolarization, depolarization, hyperpolarization. So this is the resting membrane potential, the depolarization. And when the potassium channels get opened more and more and more, you can't stop it suddenly, right? So it will get closed slowly. So it will keep, closing, but not all potassium channels are closed yet. So that's why you see hyperpolarization, and then it will come back to resting membrane potential. So this is the hyperpolarization, and that happens in most of the cells in our body.
But not the heart.
Not the heart. Okay, now we'll talk about the autorhythmicity and contraction. So we have talked about the mechanism of contractility or contraction. Now autorhythmicity and contraction. As I have explained you, hormone is self and rhythm regular intervals. So heart beats at regular interval, and the conductive system of your heart controls that. And if you see the conductive system, what is conductive system? I have mentioned that highly specialized tissue, right, in the heart, inside the heart. So that tissue is different than heart muscle, right? So the depolarization and depolarization that I have just explained to you, that is in the heart muscle, But if you see the depolarization and repolarization in conductive tissue, that very highly specialized tissue, it is different than heart muscle. How it is different than heart muscle in conductive system? If you see the depolarization here, this is the depolarization in the conductive tissue. Is it very fast or slow? Slow compared to the heart muscle, right? Heart muscle is, they have said, very fast. This is taking more time. So, the first part of depolarization, number one here, this one occurs due to the opening of sodium channels. But what type of sodium channel should work here? Voltage gated or non-voltage gated? Non-voltage, because we know that non-voltage opens slowly. Okay, so in conductive tissue, the depolarization will start because of the opening of slow non-voltage gated sodium channels. So it will go out slowly, and then when it will reach to a certain level, that is called threshold. So that certain level is called the threshold. When it will reach to the threshold, then calcium channels will get opened. So calcium influx will occur. So this part will occur due to the calcium channel opening. But calcium is also positive, right? So positive is getting in, so it will go further out. And then the repolarization is same as the cardiac muscle due to the opening of potassium channels. Okay, so potassium will get out and repolarization will occur. And then next depolarization will start. But this depolarization, as you know, the first part of depolarization is slow. That is very important. This is called the pacemaker potential. This doesn't happen in heart muscle, right? The slow first part of depolarization. Why is that? This one is giving some time between two depolarizations, giving more time, right? It is giving more time, this one, giving more time. And that is very important. You know that your conductive system, pacemaker is a part of conductive system, that's a node that produces the electrical impulse, right? I said that production of electrical impulse is one function. Now, if electrical impulse is produced extremely fast, then your heart will beat extremely fast, right? And that is dangerous because your heart chambers will not get enough time to complete the contraction and relaxation. So we need some time between the electrical impulses, because electrical impulse will tell the heart to contract. Okay? So if you don't give time, then your heartbeat will be very fast, extremely fast, right? So that's why this timing, pacemaker potential time is very important. So one impulse, then another, like 70 times it will produce in 1 minute. But if this slow is not here, then it will be more. So that is not good. That will not allow your heart to complete the contraction and relaxation. So in the test, if I ask you that the depolarization in heart muscle occurs due to what? Due to the opening of voltage gated sodium channels. In case of the conductive tissue, the depolarization occurs due to the opening of non-voltage gated sodium, first part, and last part is due to the opening of the calcium channels, right? Plateau occurs due to the opening of calcium and potassium. Calcium is getting in, potassium is getting out, so it will stay straight. Okay? And repolarization for both cases will occur due to the opening of the potassium channels. So potassium will get out. Is it okay, Karen?
Yep.
Okay. Now we'll talk about the conductive system of the heart. Highly specialized tissue is the conductive system, and that tissue forms two types of structures. That tissue forms two nodes. Nodes are round structures. Okay, so those two nodes, one is called the SA node, the upper one, and the lower one is called AV node. SA is sinoatrial node, AV is atrioventricular node. So conductive tissue forms two nodes or small round structures and a number of bundle of fibers. So if this is your heart, I'm not good in drawing, you know that. Trying to draw the heart, not good. Okay, whatever. So it's the interventricular septum, not too bad. Interventricular septum. Okay. So here. Okay, so this is right atrium, this is left atrium, left ventricle, right ventricle, okay? So, both, and here is the partition between atrium and ventricle. So, both SA node and AV node, they are located inside the right atrium, okay? Right atrium, remember that? Both SA node and AV node. Do you have any question?
I was just wondering, are they big enough? Are they visible when you look at the heart? Or are they so small you can't see them?
The SA node is visible,
SA
you can
node
see,
is
yes.
visible.
Very tiny, but visible. Yeah. So both SA node and AV node are located where? Inside the right atrium. Okay. SA node is located in the upper part of right atrium, where the superior vena cava enters. You know that superior vena cava comes from the upper part. So upper part of the right atrium we have SA node, and the AV node is close to the valves, atrioventricular valves here, okay, but still inside the right atrium. And then the SA node is connected to the AV node by fibers, and these fibers are called internodal. Makes sense, right? Inter what? Nodal. Internodal fibers in between the nodes, between SA node and AV node. And also from SA node, some fibers go to the wall of the atrium, atrial wall. Go to the atrial wall. Okay. So when SA node will produce the electrical impulse, the electricity will go from SA node to AV node, and some electrical impulse will go to the wall of the atrium. Okay. Now, from the AV node, a bundle of fibers, pretty thick bundle of fibers, will go down through the interventricular septum. This is the interventricular septum. So, will run through the interventricular septum, and this bundle of fibers is called bundle of His. Interesting name, right? Bundle of His. Present in the upper part of interventricular septum. Is it clear? Okay. Now, at the lower part of interventricular septum, this bundle of His will branch into two. How many branch? Two. Okay. Those two branches are called bundle branches. So we divide and will form bundle branches. Branches of bundle. Branches of bundle or bundle branches. And those two, this is the wall of the ventricle. So from those two branches, the fibers will enter into the wall of the ventricle and will branch many, like trees. Trees have many branches. So the bundle branches will turn like this and will enter into the wall of the ventricle and will branch like tree, and this is called Purkinje. I believe I'm correct. Purkinje fibers. Okay. So this is the conductive system of the heart. has two nodes, SA node and AV node, and a number of fibers, bundle of fibers. Okay, or fibers stacked. Okay, so from SA node the signal will go to the AV node, and then through the bundle of EEG it will go down, and then through the bundle branches go further down and will enter into the wall of the ventricle. And from the SA node, some electrical impulse will directly go to the wall of the atria. Okay. Now, what's the function of SA node? SA node is called the pacemaker of the heart. Who is the pacemaker? SA node. Why it is called the pacemaker? Because our normal heart rate is controlled by SA node or given by the SA node. SA node produces electrical impulse at a rate of normal heart rate. If your heart rate is 70, that means your SA node is producing 70 impulses in each minute. Make sense? Every time your SA node will produce electrical impulse, your heart will contract. Okay? So SA node is giving the normal heart rate or heartbeat. That's the pacemaker of the heart. Now, if SA node fails, if SA node is damaged or destroyed, or SA node cannot produce the impulse, then the AV node will take over. It's like boss, top boss, and second boss in the office, right? If top boss is there, second boss has no power to control. But if top boss is not there, then second boss will take over, right? So SA node is the boss and AV node is the lower boss. So if SA node is destroyed or non-functional, then AV node will take over and will produce electrical, will control the heart. But the AV node produces impulse at a rate of 50, around 50 per minute, so much slower than SA node, right? So in that case, what will be the heart rate? 50 or so. And now you just think that what happens actually, if two trains are running on one track, one line, two trains, the front one has 50 miles per hour, and behind one has a speed 70 miles per hour. Then both are running. Then the front one will lose its control. Who will control the whole thing? The back one, right? 70. Same thing happens. The SA node is sitting above, AV node is below. Every time AV node starts to depolarize like this, SA node sends signal. Depolarization is completed in SA node because it is faster. It will tell AV node that you don't need to do, and it will die. Okay, so the SA node is every time sending signal to the AV node and making it making the AV node inactive. Okay, that's why SA node controls the heart rate.
So it never goes above threshold?
Never
Maybe.
goes above. Yeah, very
Well,
good.
in normal circumstances.
Exactly. So before it reaches to the threshold, it will die. Okay, it will be inhibited. Okay, so just know those parts of the conductive system and the function of SA node and AV node. The fibers mainly transmit the electrical impulse. Okay, so in this picture you can see the conductive system of the heart, and those parts I have explained to you. Now we'll talk about the abnormal heart function. First, this is the normal sinus rhythm. That means normal EKG, normal heart function. And when we record the EKG, it will look like this: PUF, then what? QRS and T. You know that those three components, right? P, QRS, and T. P represents what? Atrial contraction. And QRS represents ventricular contraction. That's why QRS is that big, because ventricular contraction is very powerful, we know that, right? Atrial contraction is weak. So P is atrial contraction or atrial depolarization, and QRS is ventricular contraction. and then T is ventricular relaxation. So which one is missing here? You got atrial contraction, you got ventricular contraction, you got ventricular relaxation. Which one is missing? Atrial relaxation is missing, right? Why you don't see the atrial relaxation in EKG? The reason is when atrial relaxation starts, at that time ventricular contraction starts at the same time. And which one is very powerful? Ventricular contraction, right? So at the same time, both happens. Atrium relaxes and ventricle starts to contract. So the tiny wave created by the atrial relaxation will be buried under the ventricular forceful ventricular contraction. Big wave, right? If you put two waves on water, if you put the big one, you won't see the small wave, right? In water. So same thing. Since at the same time two waves are being created, small and big, the big one will be formed to listening, the other one will be mass. Okay. Anyway, so now junctional rhythm is called first degree heart block or blockage, and that is what if SA node becomes non-functional. Now you tell me, you will understand it easily. If SA node is non-functional, then what will be your heart rate?
50.
50. Very good. So the interval between the EKGs will be longer, right? Because heart is beating less. The heart rate is less, so the interval will be longer. Number one. Number two, from SA node, the signal, electrical signal goes to the wall of the atrium, that I have mentioned many times. So to the wall of the atrium. So atrium will not get any electrical signal, right? So atrium will not contract, because to contract it needs the electrical signal. So atrium will not contract. So which wave will be missing? P will be missing. Make sense? Because P represents what? Atrial contraction. So P will be missing from the EKG. You won't see P. Number one, you will see the interval is bigger. Okay, so those two things you will see in junctional rhythm. In second degree heart block, what happens? The AV node is partially damaged or non-functional or blocked. Okay, so if it is partially destroyed, then what will happen? The signal from SA node will go to the AV node, but the signal from AV node that will get out will not be strong, right? Weak, because many tissue fibers have been destroyed here, many cells have been destroyed here. So weak signal will go there to the wall of the ventricles. Make sense?
Yeah.
So in that case, you will see the QRS complex will get smaller because the ventricle will contract quickly. Makes sense? Because it's getting less signal. So it will get smaller. So that what we see that P wave is normal, but QRS gets smaller. Okay? That happens in second degree. And another condition that is called ventricular fibrillation. And think that which one is more dangerous, first degree or second degree? Second degree is dangerous because ventricular contraction is very important. Remember that ventricular contraction is, forceful contraction is very important. Now, ventricular fibrillation. The term fibrillation means uncontrolled, irregular heartbeat. So, very also high frequency. So you add those three: high frequency, uncontrolled, irregular heartbeat. Okay? Contraction of the heart wall. Now, ventricular contraction means the wall of the ventricle will contract in high frequency, very high rate, and irregular. Irregular means we know that heart should contract in rhythmic way, right? In regular interval. But in that case, it will beat very fast, and maybe sometimes it will very fast, then get slow, and then again very fast. So that's not rhythmic, right? So high frequency, irregular, uncontrolled contraction. That's the fibrillation. And fibrillation can occur both in the wall of the atrium as well as in the ventricle. If it happens in the wall of the atrium, that is called atrial fibrillation. If it happens in the wall of the ventricle, that is the ventricular fibrillation. Which one is dangerous? Ventricular fibrillation is dangerous. Atrial fibrillation is not that dangerous. It happens very often, we hear that, but that's not very harmful. Okay, the term arrhythmia. Arrhythmia indicates irregular heartbeat. So, if you the term arrhythmia is a broad term, that means it indicates irregular heartbeat. Irregular could be, heartbeat can be very high or could be very low, right? Both are irregular, not regular, not normal. So if the heart rate is very high, that is called tachycardia. Tachycardia, increased heart rate. And if you see the heart rate is lower than normal, that is called bradycardia. So tachycardia is high heart rate and bradycardia is low. So both are arrhythmias. Fibrillation, I have already explained to you, fibrillation. And ectopic focus. If we know that pacemaker produces the impulse and the heart beat depends on that impulse, how many times, right? Now, if the electrical impulse is produced anywhere else outside of the pacemaker, outside of SA node, that is called ectopic focus. What happens is the heart muscle, if this is the wall of the ventricle, sometimes some heart muscle cells, they become, capable to produce electrical impulse, electricity. And in that case, when you will see the normal EKG, this is P, QRS, and T. This is due to the normal pacemaker function. Now, if just think that this tissue is producing electrical impulse, then what will happen? This part of heart muscle will contract, right? Will produce a weak contraction. So this is ventricular contraction. So you will see an extra component in the EKG. Makes sense? Because the ventricular wall itself is creating some contraction. Okay? So an extra contraction you will see here. So that is the ectopic focus. Anywhere outside of SA node, if the electrical impulse is produced and that causes an extra contraction, that is the ectopic focus. And we have talked about the heart blocks. Now we'll talk about the regulation or control of the heartbeat. There are two cardiac centers present in the medulla oblongata. In the brain stem, you know that the medulla oblongata, the brain stem, and there are two cardiac centers. One is called cardio-acceleratory center, and another is called the cardio-inhibitory center. Okay, so cardio-acceleratory and cardio-inhibitory centers. It's like your car. Your car has what? Accelerator and brake, right? Brake is the inhibitor. So you have two centers in your medulla oblongata. When accelerator center will be stimulated or will be activated, your heart rate will do what? Go up, because it is accelerator, right? Acceleratory center. It's like your car will go fast, your heart will go fast. And when the cardio-inhibitory center will be stimulated, your heart rate will get slower. Okay, good. Now, from those centers, the nerves carry the signal. Someone has to carry the signal, right? Because brainstem is in your medulla oblongata inside your brain. From there, someone has to take the signal to the heart, right? So from the cardio-excitatory center, the sympathetic nerve fibers will take the signal to the heart. And from cardio-inhibitory, the parasympathetic fibers will take the signal to the heart. You remember in NP1, I have talked about sympathetic and parasympathetic, and I told you the best example of sympathetic activation is what? When you are excited. You remember that? You are excited, you are watching a movie that has a lot of suspense, right? What happens? Your heart rate increases, right? So sympathetic activation will increase the heart rate. Sympathetic nerves will take the signal to increase the heart rate. And I told you, if you are relaxing, you are watching golf, right? You remember that? Your heart rate will go down. Your parasympathetic system will be activated, right? So, from the acceleratory center, sympathetic nerves will take the signal to the heart, and sympathetic activation will increase, sympathetic will increase, right? And parasympathetic will come from the inhibitory center to the heart to slow down, decrease the heart rate. Okay. Now, the main parasympathetic nerve in our body is the vagus nerve. Vagus is the main parasympathetic nerve. Okay. So, the signal will be taken to the heart mainly by the parasympathetic signal. Inhibitory signal will be mainly taken by the vagus, which is the main parasympathetic nerve in our body. Okay, so now if you see this picture, it will make sense. So, these are the pieces of medulla oblongata, and this is the cardio-inhibitory center. Cardio-inhibitory center, and from the cardio-inhibitory center, the parasympathetic, the vagus, will take the signal down to the heart. Where? To the SA node and AV node. Because we know that SA node is the main thing, right? That is controlling the heart rate. So if you can slow the SA node, heart rate will go down, right? But signal also goes to the AV node, inhibitory signal. And from the cardio-acceleratory center, the sympathetic nerve, here cardio-acceleratory center, the sympathetic nerve will take the signal to the heart, and signal will go to SA node, AV node, as well as to the wall of the ventricle, okay? And will tell the heart to beat more, increase the heart rate, okay? So that's the main thing here. Do you have any questions? No? Okay. Electrocardiography or EKG. You have seen that each EKG has 3 components or events. I have mentioned many times: P, QRS, and T. P wave, QRS complex, and T wave. And if you see here, those 3 components are events. Okay, and from the EKG, we can measure the number of durations or intervals, and by measuring those, we can tell how long the atrium took to complete the contraction, right? How long the ventricle took to complete the contraction. What was the interval between the atrial contraction and ventricular contraction, right? Ventricular contraction and ventricular relaxation. We can measure all those things, right, from the EKG. And those information are very important, because if you know the normal intervals and compare it to the patient's interval, then you can tell where is the difference, right? And you can look that one more carefully. That problem is here. That problem is here. You can do that by measuring those intervals or durations. That's the main purpose of the EKG, the durations or intervals. Another information you get from here, that's the amplitude. How tall the waves are. As I told you, if the contraction is more forceful, the amplitude will be higher, right? The length will be, the height will be more. Make sense? That's why you see ventricular contraction goes that high, because you know that ventricular contraction is very close. So we've got two types of information here. One is we can measure the intervals or duration. Another is we can measure the length, measure the height to see how forceful the contraction is, right? The amplitude. So those both information we can get from the EKG. This one is a nice picture showing different events and what's going on during those events inside the heart. So we know that SA node produces electrical impulse, and that is spreading here in the wall of the atrium, and atrial depolarization will occur. So that is the P wave. So when the atrium will be depolarized during this time, the P wave will be created. Then here atrial depolarization is completed. So P wave is completed, it is done. Then the trace will come here, the line will come here on the screen. And then after that, ventricular depolarization will start. And so this one will start, and when it will spread throughout the wall of the ventricle, ventricular depolarization will be completed, and then you see here the ventricular depolarization has been completed, so this one has been completed, then the line will come here. Okay, so we are done this part. You won't see that anymore, you will see it here. And then the ventricular relaxation. The red color is showing the relaxation, and ventricular relaxation is indicated by T. You will see the T wave during the ventricular relaxation. Here relaxation is completed, so T is completed. Okay, the line will come here. So very nice picture showing that what's going on inside the heart and the waves representing that. Okay, so we'll stop here. We'll talk about the blood pressure in future lectures. So just stop here. And your lecture exam will include the materials covered until today. Okay? From the beginning to today.
No study sheet. No study sheet. The slides or study sheet.
Yeah, you have taken the class notes and go over the slides and notes, okay? You should get one.
Professor, fill in the blank, choice, or the bottom.
Almost all of them are multiple choice, and there could be only few short answers or few.
Yeah, we just everything.
And
There could be one picture.
oh, great.
There will be one picture.
Could be.
Which picture? Yeah.
What's the deduction for spelling then? The deduction for spelling?
Multiple choice.
If I, minor things, I understand. If it's like, if it's cow, and they will write sheep, that means sheep.
Then, okay, yeah. Well, that's a wrong answer anyway, so, okay, okay.
Thank you.
Are you watching this?
Oh, yeah, I will.
No, we go to the game.
I will be studying.
Study today, tomorrow.
Oh, no, I have to study all weekend. Yeah.
I'm actually having some people over for the Super Bowl,
Oh, I have just.
so yeah, so I've got to make sure I study.
Yeah.
Here early, Monday morning.
You're inviting somebody at your house, or
I'm having,
people are coming from
yeah, I'm having
party?
some family and a couple of friends,
Huh?
and
Is
then,
it crazy?
so yeah, so I gotta make sure I do my study
Yeah.
before then,
You
yeah.
have to cook the food. but-
I got another test on Monday, and then I got another one on Tuesday.
Yes.
I got the flight my time.
Yeah, it was sweetie this morning.
Yeah.
Yeah, but I